Ionization enthalpies. Generally, the ionization enthalpy increases along a series as a nuclear charge increases for the transition elements. And the ionization enthalpies of D block elements lie in between S block and P block elements. They are higher than those of S block elements and are lesser than those of P block elements. Their regular increase, they have some irregularities in case of first transition series as well as in second and third transition series. This irregular trend in first ionization enthalpy of first transition series, that is 3D series, is due to the fact that removal of the electrons alters the relative energies of 4s and 3D orbitals. If we remove the electrons from 4s and 3D orbitals, their energies changes, and this is called as reorganization energy. Reorganization energy, which is accompanied by the ionization, and this results into the release of exchange energy, which increases as the number of electrons increases in the dn configuration, and also from the transference of s electron to the d orbitals. For example, chromium has the lower ionization, first ionization enthalpy, because in case of chromium, its electronic configuration is 3d5 4s1. If chromium lost its one electron, it left with 3d5 configuration, which is exactly half-filled configuration or stable configuration. That's why it has the lower first ionization enthalpy in its series. And zinc has very high ionization enthalpy, because in zinc it has fully filled D configuration as well as 4s2. 2 is also fully filled. It has fully filled configuration. That's why it is more stable and hence require more energy to remove the electron from the outermost shell. Next is the first ionization enthalpies of zinc, cadmium and mercury are however very high because of fully filled d orbitals as well as s orbitals, means they have stable configuration. Although the second and third ionization enthalpies also in general increase along a period, but the magnitude of increase for the successive element is much higher. For example, second ionization enthalpy of chromium to manganese and from copper to zinc, like second ionization enthalpy, vanadium is lower than chromium and chromium is also higher than manganese. Second ionization enthalpy of chromium is higher than vanadium as well as manganese. Vanadium has atomic number of 23. Its outer electronic configuration is 3d34s2. In case of chromium 24, it has 3d5 4s1, and in case of manganese it is 25 here, it is 3d5 4s2. If we remove first electron from 4s orbital of vanadium, it requires less energy because it is far away from the nucleus and the electron is loosely bound. And in case of chromium, it is also easy to remove the electrons, but its energy is higher than that of vanadium due to effective nuclear charge. As the atomic number increases, effective nuclear charge also increases. Similarly for the case of manganese for first ionization enthalpy. But for second ionization enthalpy, here we left with one electron, and this one electron is get easily removed from this 4s orbital. But in this case, we have to remove the electron from 3d orbitals, which has exactly half-filled configuration, and it requires more energy to knock out the electron from exactly half-filled configuration, means stable configuration. And in case of manganese, we left with 4s1 electron, and we can easily remove this electron, second electron. That's why magnesium has the lower ionization enthalpy than chromium. And in case of third ionization enthalpy, that is from iron Fe2 positive to Fe3 positive. Here it is Fe2 positive, iron atomic number 26, outer electronic configuration is 3d6 4s2. When we remove the 2 electrons, we left with 3d6 electrons, and when we remove the third electron, we left with the 3d5, which is a stable electron, stable exactly half-filled configuration. But in case of manganese, if we remove these 2 electrons from 4s, and we left with 3d5 configuration, which is exactly half-filled configuration and stable configuration. And for removing third electron from 3d orbital, we require more energy. That's why manganese has higher third ionization enthalpy than iron Fe3 positive. The first ionization enthalpies of 5d series are higher than those of 4d and 3d elements. This is due to the poor shielding effect of 4f electrons. This is due to the poor shielding effect of 4f electrons, because in 5d series there are 4f electrons in the elements, and they have poor shielding effect. 4f electrons, they have poor shielding effect than d orbital, than d electrons, and p electrons, than s electrons. and that's why the outermost electrons are more strongly held by the nucleus, and we require more energy to remove the electron from the outermost shell. That's why it's higher ionization enthalpies for 5D series as compared to 4D and 3D series.